ASAP allows you to model both surface as well as volumetric scatter to get a true idea of what's happening as any light propagates through your optical system. Let's take a look at defining volumetric and surface scatter within an ASAP model. Let's start by talking about volumetric scatter. Volume scatter is very important for a lot of applications, especially in the area of biological sciences. What happens when light propagates through biological tissue, skin, blood, etc. Within ASAP, we can model volumetric scatter using a volume scatter definition and applying that definition to our media. In this particular case, what we're doing is applying a scatter profile, if you will, to a volume of water. And then we've defined a volume to contain that water, and we're going to look at the light as it propagates through that system. So let's take a look at the file. Within ASAP, you can decide what the preferential direction of the scatter is. Is it in a 360-degree sphere? Is it preferentially in a forward direction? Is it preferentially in a narrow direction? You can also ask ASAP to capture data at different locations within your system so you can get information about how much light directly transmitted through the system, how much transmitted but was diffused or scattered, and how much light was reflected as it propagated through the system. We can also get information about the angular distribution of the energy as it leaves the system as well. So any type of information is available to you, and you can define any type of volumetric scatter. You can define the size of the particles, you can define the particle density, the cross-sectional area covered by the particles, all of which will allow you to do an accurate simulation of volumetric scatter. Surface scatter is also important. We often talk about nice smooth surfaces like lenses or mirrors or windows, but the reality is all of our surfaces are somewhat rough. And if we don't take into account that roughness, then we won't really get an accurate simulation of what happens to our optical system or within our optical system. And this is a very simple demonstration of this. Let's take a look at what happens to light that's reflected off a parabolic surface when we've got a source somewhat near the focus, although it is an extended source. When we assume first off that the surface is perfectly smooth, and secondly, we're going to apply a roughness to it. So let's take a look first at a perfectly smooth surface. And what we see is a nice concentration of energy, as typical as we'd expect in this particular case. What we've got is a filament at the focus of the parabola, so we can see the effect of the filament, and we can see the light that comes out from all of the surfaces of the parabola. Now let's see what happens when we make that parabola surface slightly rougher. And I've got a roughness model defined using a Harvey parameter model, and we made that a rougher surface, and let's see what the output looks like just outside the surface. And as you can see, it is a significantly larger distribution of energy, and this is due to the fact that as the rays strike the roughened surface, the rays can be scattered in any direction. So this is what the smooth surface leads us to believe we have at the output, and this is what a more realistic approximation looks like. So again, within ASAP, whether you need to model surface scatter, volumetric scatter, or both, all of the capabilities are included with the software.